Hi students, welcome to the 9th lecture in permutations and combinations. I hope you have watched the first 8 lectures. In this lecture we are going to deal with permutations with constraint repetitions. I will explain what do you mean by permutations with constraint repetitions shortly, but before looking into this one, let me recall what we have done in the first 8 lectures. The first 8 lectures we have discussed about fundamental principle of counting, both multiplication and addition. So if a task can be performed in if a task can be divided into two works, W1 and W2, then the number of ways of completing the task is equal to number of ways of completing W1 times number of ways of completing W2. And if a task can be performed in two formats, W1 or W2, then the number of ways of completing the task is equal to number of ways of completing W1 plus number of ways of completing W2. So here what you have to remember is whenever n comes you have to multiply, whenever r comes you have to add. So these are the two things that you have to remember throughout this chapter. And then we have defined factorials, and then we have defined linear and circular permutations. So if you arrange things in a line, then it is going to be a linear permutation. If you arrange things on a circle, then it is going to be a circular permutation. And then we have counted number of linear permutations of n. Number of linear permutations of n distinct objects taken r at a time is in general denoted by npr, and npr is equal to n factorial upon n minus r factorial. These are the total number of permutations of n distinct objects taken r at a time. And we have seen few results related to this one. npr is equal to n times n minus 1 pr minus 1, and npr is equal to n minus 1 pr plus r times n minus 1 pr minus 1. This r times n minus 1 pr minus 1 stands for number of permutations of n distinct objects taken r at a time, which always include a particular element. This one n minus 1 pr stands for number of permutations of n distinct objects taken r at a time without including a particular object. This npr stands for number of permutations of n distinct objects taken r at a time. Therefore, total number of permutations is equal to number of permutations in which a particular object is not there plus total number of permutations in which a particular object is always there. Next, when repetitions are allowed, then the number of permutations of n distinct objects is taken r at a time is n raised to r. So this is the result when repetitions are allowed. When repetitions are not allowed, then the number of permutations is equal to npr, which is equal to n factorial upon n minus r factorial. When repetitions are allowed, then the number of permutations is going to be n raised to r. The total number of permutations in which at least one repetition is there is equal to n raised to r minus npr. N raised to r gives the total number of permutations, npr gives the number of permutations in which repetitions are not there. Then number of permutations with at least one repetition is equal to total minus number of permutations without repetitions, which is n raised to r minus npr. And then we have seen this definition of palindrome. So if you read from left to right or from right to left, it gives the same meaning. The number of palindromes of n distinct objects of length r is going to be n raised to r upon 2 if r is an even number, and n raised to r plus 1 upon 2 if r is an odd number. So depending upon the number of digits, we will use these formulas. If the number of digits is going to be even, we will use the first one, that is n raised to r upon 2. If the number of digits is going to be okay. And then we have seen number of circular permutations. Number of circular permutations of n distinct objects taken all at a time is equal to n minus 1 factorial. I repeat, the number of circular permutations of n distinct objects taken all at a time is equal to n minus 1 factorial. See, here we have n minus 1 factorial because a few linear one circular permutation results in n different linear permutations. Therefore, the total number of circular permutations is going to be n factorial upon n, which is nothing but n minus 1 factorial. So in case of hanging models, that is in the case of chain of beads or garland of flowers, both clockwise and anti-clockwise permutation should be treated as a single permutation. Therefore, the total number of permutations is going to be n minus 1 factorial upon 2. Since we are identifying clockwise and anti-clockwise permutations as a single permutation. Since we are identifying two permutations as a single permutation, we have to divide it by 2. So otherwise we don't have any division. Only in case of hanging models we have to divide. Now let us try to answer these questions. Find the number of ways of arranging the letters of the word A and T. So here I can use this formula NPR. Number of ways of arranging the letters of the word A and T is going to be, so here 3p3, which is equal to 3 factorial. So the number of ways of arranging the letters of the word A and T is going to be 3 factorial. Now let us try to answer the second question. Find the number of 3-letter words that can be formed using the letters of the word A and T when repetitions are allowed. So when repetitions are allowed, we have this formula n raised to r. So here my n is equal to 3 and r is equal to 3. So number of 3-letter words is going to be 3 raised to 3, which is okay. Okay, let us try to answer these questions. Find the number of permutations of the letters of the word DAD, and the next one is EAMCET, EAMCET, and the next one is Ramana, RAMANA. So if you observe here, the letters are not distinct. If the letters are distinct, then I can use this formula NPR. Here I have to use A only one time, and here I can use D 2 times. That means I can repeat D. So as I can repeat D, I cannot use this formula n raised to r, because here I am not supposed to repeat A, and I am not supposed to repeat A more than one time, and I am not supposed to repeat D more than 2 times, nor I am not supposed to use D less than 2 times. I have to use D exactly 2 times and A exactly 1 time. So in order to answer these questions, I cannot use this formula NPR, nor I cannot use this formula n raised to r. So these kind of problems come into the category of permutations with constraints. Permutations with constraints. So our next goal is to count how many such permutations are there, or what is the formula for number of permutations when there are some constraints like this. So here we have to calculate number of permutations of the letters of the word DAD, and number of permutations of the letters of the word EAMCET, and the number of permutations of the letters of the word RAMANA. So these kind of problems we haven't seen so far. So I cannot use this formula NPR, or I cannot use this formula n raised to r. So I can use this NPR formula only if repetitions are not allowed and all the objects are distinct. I can use this formula only when all the objects are distinct and repetitions are allowed. So here in these problems, we are repeating certain letters and we are not repeating certain letters. So all the objects are not distinct and we are not repeating any number of times. We are not repeating any letter any number of times. So I cannot use the first one, nor I cannot use the second one. So we have to develop a formula to find out number of such permutations. And the number of such permutations is given by this theorem. And the statement of the theorem is like this. The number of permutations of n objects in which the number of permutations of n things in which p things are alike and the remaining are not alike is going to be n factorial upon p factorial. The number of permutations of n objects or n things in which p objects or p things are alike and the remaining are not alike is going to be n factorial upon p factorial. We can give the proof of this theorem, but before going into the proof, let us try to understand this using an example. Okay, so in the example problem is like this. Find the number of permutations of the letters of the word SEEE. So here we have four distinct letters or four letters. Out of these four letters, three are alike. We have three E's which are alike. So all the objects are not distinct here. Now what we do is we'll try to convert this problem into a problem which we are familiar with. We are familiar with those problems in which all the objects are distinct. So here what we are doing is we'll treat these three E's as distinct E's, namely E1, E2 and E3. I will treat these three E's as different E's. So namely E1, E2 and E3. Now we have the following permutations. So if you treat these three E's as distinct E's, we'll have four distinct letters. So using those four distinct letters, we have 4 factorial distinct permutations. And these are my 4 factorial distinct permutations. Now what happens if you treat these three E's as same E's? Then what we'll have is, this is my first permutation SEEE, and the second permutation is going to be ESEE, and the third permutation is going to be EESE, and the fourth permutation is going to be EES. Since it is a small problem, I can list down all the permutations, and out of all the permutations I can treat the required permutation. I can take the required permutation. So the required number of permutations is going to be 4. So these are my 4 permutations. So here I am treating these three E's as similar E's. What happens if I treat these three E's as distinct E's? If I treat these three E's as distinct E's, then I am going to get these 3 factorial permutations. So this single permutation yields 3 factorial different permutations, or this single permutation gives rise to 3 factorial distinct permutations. If you treat these three E's as distinct E's. And similarly, this single permutation gives rise to these 3 factorial permutations. And this single permutation gives rise to these 3 factorial permutations, and this gives rise to these 3 factorial permutations. On the whole, we have 4 factorial permutations. But out of which every we are identifying 3 factorial permutations as a single permutation. We are identifying these 3 factorial permutations as a single permutation, or else the total number of the total money which I have is 4 factorial, and I can buy one pen using this 3 factorial rupees, and I can buy this pen using this 3 factorial rupees. So how many pens I can buy? The total is equal to 4 factorial, and the cost of each pen is going to be 3 factorial. Therefore the number of pens I can buy is equal to 4 factorial upon 3 factorial. So here also the same thing. The total number of permutations is 4 factorial, and these 3 factorial permutations results in a single permutation. Therefore the total number of permutations is going to be 4 factorial upon 3 factorial. So which is equal to 4, and these are my 4 distinct permutations. So if you observe the technique here, we can give the proof of the theorem. So here what we are doing is we are treating these 3 E's as distinct E's. If you treat these 3 E's as distinct E's, then we will have total 4 letters, and I can have 4 factorial permutations. But the given data is not like this. The 3 E's are alike. So we have to treat these 3 E's as alike objects. Now if you treat these 3 E's as alike objects, then these 3 factorial permutations results in a single permutation, or this single permutation gives rise to these 3 factorial permutations if you treat these 3 E's as different E's. Therefore the total number of permutations is going to be 4 factorial upon 3 factorial. Okay. Now let us try to give the proof of this theorem. First let us write down the data. We have n objects, out of which p are alike. P are alike means the remaining n minus p objects are distinct. Now we have to find how many permutations we can form using these n objects. Let the number of permutations be, let the required number of permutations be m. Required number of permutations be m means the number of permutations of n objects in which p objects are alike be m. Now we have to find out what is this m. Now one single permutation here gives rise to p factorial permutations. To p factorial permutations, if we treat those things, those p alike things as distinct. If you treat those p alike things as distinct objects, then the single permutation gives rise to p factorial permutations. So in the previous problem also, this single permutation SEEE is giving rise to these 3 factorial permutations. So why we are having these 3 factorial permutations means we are having 3 different E's, 3 alike E's. So if you treat these 3 alike E's as 3 distinct E's, then we are going to have these 3 factorial permutations. So here also one single permutation gives rise to p factorial permutations, if we treat those p alike things as distinct objects. Now the total number of permutations which we have is m, which gives rise to m times p factorial permutations. If we treat those p things as distinct, once we treat those p things as distinct objects, this implies now we have n distinct objects. Now we have n distinct objects. So why we have n distinct objects? We are treating those p objects as distinct objects. In the data we have p alike things, but here we are treating those p alike things as distinct objects. Once we treat those p alike things as distinct objects, the number of objects is going to be n and all the objects are different. Okay. Number of permutations is equal to number of permutations of these n objects is equal to n factorial. But we know that number of permutations is equal to m times p factorial. So this implies m times p factorial is equal to n factorial, or m is equal to n factorial upon p factorial. So this is the proof. So let me repeat the proof for you. So we have n distinct n objects, out of which p objects are alike. Now we have to find the number of permutations in this case. So let the number of permutations in this case be m. One single permutation gives rise to p factorial permutations, if we treat those p objects as distinct objects. So on the whole we have m permutations. So this m permutations gives rise to m times p factorial permutations if you treat those p objects as distinct objects. If you treat those p objects as distinct objects, then the number of distinct objects that we have is n. Now using those n distinct objects, we can have n factorial permutations. But the total number of permutations here is m times p factorial. Therefore m times p factorial must be equal to n factorial, or m is equal to n factorial upon p factorial. That is, that number of permutations of n objects in which p objects are alike is going to be n factorial upon p factorial. So once we establish this formula, we can answer these questions. The number of permutations of the letters of the word DAD is going to be 3 factorial upon 2 factorial, because here we have 2 D's, and the number of permutations of the letters of the word EAMCET is going to be 6 factorial upon 2 factorial, and here the answer is going to be 6 factorial upon 3 factorial, because here we have 3 alike objects. Okay. Now let us try to answer these 2 questions. Then find the number of permutations of the letters of the word GOOD. So here the number of permutations, here we have 4 letters, out of which 2 are alike. Therefore number of permutations is equal to 4 factorial upon 2 factorial. Okay. Now let us try to answer this question. Find the number of ways of arranging 2 identical balls into 10 different boxes. Or if I say 10 boxes, you have to treat those 10 boxes as distinct boxes. When we don't mention anything, you can treat those objects as distinct objects. So if the objects are alike, then we will mention it. Okay. So what we do here is we'll try to convert this problem into a known problem. Known problem in the sense we'll treat those 2 balls as distinct balls. Number of ways of arranging 2 distinct balls. 2 distinct balls into 10 boxes. 10 boxes means 10 distinct boxes is equal to 10p2. So why we have this 10p2 means this problem is same as number of ways of arranging 2 people in 10 chairs. So in how many ways I can arrange 2 people in 10 chairs? The first person can be arranged in 10 ways and the second person can be arranged in 9 ways. 10 times 9, which is nothing but 10p2. So here also the number of ways of arranging 2 distinct balls into 10 distinct boxes is going to be 10p2. But here the balls are not distinct. They are identical. Therefore, total number of arrangements is equal to is going to be 10p2 upon 2 factorial. Because we are treating those 2 balls as identical balls. Therefore, the number of arrangements is equal to 10p2 upon 2 factorial. So here also in this theorem statement, we have n factorial upon p factorial. Why we have this n factorial means we are treating those n objects as distinct objects. If you treat those n objects as distinct objects, then we have n factorial. But out of which p objects are alike. So p factorial permutations result in a single permutation. Therefore, we are treating those p factorial permutations as a single permutation. So we have n factorial upon p factorial. So here also we have this result. So if you treat those 2 balls as distinct balls, then the number of ways of arranging those 2 balls into 10 boxes is equal to 10p2. But here these 2 balls are identical balls. Therefore, the total number of arrangements is equal to 10p2 upon 2 factorial. Okay. Let us try to answer this question. Find the number of ways of arranging the letters of the word BA, BA. So here we have 4 objects. Here we have 4 objects, out of which we have 2 A's and 2 B's. So these 2 A's are identical A's and these 2 B's are identical B's. So here we have two sets of identical things. If we have one set of identical things, then I can use this formula, n factorial upon p factorial. But here we have two sets of identical things. So if you have two sets of identical things, then I cannot use that formula. So I have to generalize that formula. So the generalization is like this. The number of permutations of n objects in which p objects are alike, q objects are alike, and r objects are alike, and the remaining are not alike, is going to be n factorial upon p factorial times q factorial times r factorial. So we have n objects. In those n objects, we have three sets of objects. The first set is consists of p alike things, and the second set consists of q alike things, and the third set consists of r alike things, and the remaining are distinct. And the number of arrangements is going to be n factorial upon p factorial times q factorial times r factorial. Because one single permutation results in p factorial times q factorial times r factorial distinct permutations if you treat all the objects as distinct. So if you have only one set of alike things, then the answer is going to be n factorial upon p factorial. If you have two sets or three sets of alike things, then the answer is going to be n factorial upon p factorial times q factorial times r factorial. Therefore here the answer is going to be 4 factorial upon 2 factorial times 2 factorial. Okay, so if you understand this result, then you can answer this question. Find the number of ways of arranging the letters of the word banana. B-A-N-A-N-A. So here we have 6 distinct letters, 6 letters, therefore the number of ways is 6 factorial. Upon, we have 3 A's, so 3 factorial times 2 factorial. We have 3 identical A's and 2 identical N's. Therefore the answer is going to be 6 factorial upon 3 factorial times 2 factorial. With this result, we have completed the concepts related to permutations with constraints. Next we have to do few problems related to these things. And the first example problem is like this. Find the number of ways of arranging the letters of the word specific. In how many of these arrangements the two C's come together and no two I's come together? First let us write down the letters of the word specific. So we have S, P, E, C, I, F, I, C. So we have two C's which are identical, and we have two I's which are identical. So on the whole we have 1, 2, 3, 4, 5, 6, 7, 8 letters. We have 8 letters in which we have two C's which are identical, and we have two I's which are identical. Now the number of arrangements is equal to is equal to 8 factorial upon 2 factorial times 2 factorial. So here we are using the formula n factorial upon p factorial times q factorial. Number of arranging n things in which p things are alike and q things are alike is going to be n factorial upon p factorial times q factorial. So the number of ways of arranging these 8 letters in which two C's are identical and two I's are identical is 8 factorial upon 2 factorial times 2 factorial. So these are the total number of arrangements without any constraints. And the first one, two C's come together. So whenever you have a problem like coming together, what you have to do is you have to tie up these two C's. So if you tie up these two C's, then how many units you have? First let me write down S, P, E, C, I, F, I, C, C. So we can treat these two C's as a single unit. Now the total number of units you have is equal to 7. Now we have 7 units. These can be arranged in 7 factorial upon 2 factorial ways. These 7 units can be arranged among themselves in 7 factorial upon 2 factorial ways. 2 C's can be arranged in 2 factorial upon 2 factorial ways. This implies total is equal to 7 factorial upon 2 factorial times 2 factorial upon 2 factorial. These are the total number of arrangements in which 2 C's come together. This 7 factorial upon 2 factorial is related to arranging these 7 units. In these 7 units, we have 2 units which are identical. We have 2 i's which are identical. Therefore, the total number of arrangements is equal to 7 factorial upon 2 factorial. And this 2 factorial upon 2 factorial corresponds to the number of arrangements of C's among themselves. So we have 2 C's which can be arranged in 2 factorial upon 2 factorial ways. If those 2 C's are different, then we have 2 factorial. But unfortunately, these 2 C's are identical, therefore we have to divide it by 2 factorial. Therefore, the total number of arrangements is going to be 7 factorial upon 2 factorial times 2 factorial upon 2 factorial. So no need to expand all these things, you can just leave the answer as it is. And the second one is 2 i's come together. 2 i's do not come together. So whenever we have a problem like this, first we have to arrange the remaining objects. So W1 is to arrange the remaining things, and W2 is to arrange the i's in the gaps. So W1 is, we can arrange the remaining letters. The remaining letters are going to be S, P, E, C, I, F, I and C. So on the whole we have first gap, second gap, third gap, fourth gap, fifth gap, sixth gap and 7 gaps. I can arrange these 6 letters in 6 factorial upon 2 factorial ways. Number of ways of doing W1 is equal to 6 factorial upon 2 factorial. Now W2 is to arrange these i's in these 7 gaps. Arrange i's in 7 gaps. So this number of ways of doing W2 is equal to 7P2 upon 2 factorial. So we have 7 gaps and we have to arrange 2 i's in these 7 gaps. We had done a problem earlier. Number of ways of arranging 2 identical balls in 10 boxes is going to be 10P2 upon 2 factorial. So here also number of ways of arranging 2 i's in these 7 gaps is equal to 7P2 upon 2 factorial. Therefore number of ways of completing the task is equal to number of ways of doing W1 times number of ways of doing W2, which is going to be 6 factorial upon 2 factorial times 7P2 upon 2 factorial. The next problem is like this. Find the number of ways of arranging the letters of the word singing so that they begin and end with I. And the next one is the 2 G's do not come together and the relative positions of the vowels and consonants are not disturbed. We have 3 parts in this question. The first part is they begin and end with I, and the second part is the 2 G's come together, and the third one is the relative position of the vowels and consonants are not disturbed. So first let us write down the letters of the word singing. So S, I, N, G, I. We have 2 I's, N, G. We have 2 N's and we have 2 G's. So on the whole we have 7 letters. So in these 7 letters we have 2 I's which are identical, 2 N's which are identical and 2 G's which are identical. Okay. So let us answer the first one. So if there are no constraints, then what is the answer? So on the whole we have 7 letters, 7 factorial upon 2 factorial upon 2, 7 factorial upon 2 factorial times 2 factorial times 2 factorial times. If there are no constraints, then the answer is going to be 7 factorial upon 2 factorial times 2 factorial times 2 factorial. These are the total number of arrangements of the letters of the word singing. But the question is not like that. So how many of them begin and end with I? So what we have to do is we have to fill the first blank and the last blank with I. This is my first blank. I have to fill it with I. Second, third, fourth, fifth, sixth and seventh. And the last blank should be filled with I. So here I am doing W1 is to fill the first and last blank with I. So this I can do it in only one way. So 2 factorial upon 2 factorial. Or else instead of writing 2 factorial upon 2 factorial, we have two places. I have to fill it with two objects, which is 2p2 upon 2 factorial. So number of ways of doing W1 is equal to 2p2 upon 2 factorial. Now W2 is to fill the remaining blanks. Now this W2 can be done. What are the remaining letters that we have? So we have finished I's, so we have 2 N's and we have 2 G's and 1 S. So number of ways of doing W2 is going to be 5 factorial upon 2 factorial times 2 factorial. Therefore total number of ways of completing the task is equal to number of ways of doing W1 times number of ways of doing W2, which is equal to 2p2 upon 2 factorial times 5 factorial upon 2 factorial times 2 factorial. So this is your answer for the first question. And the next one, the two G's come together. Two G's come together means we have to tie up two G's. So tie up two G's. So after tying up two G's, so we have 6 units. So we have 6 units. So these 6 units can be arranged among themselves in 6 factorial upon 2 factorial times 2 factorial. These 6 units can be arranged among themselves in 6 factorial upon 2 factorial times 2 factorial. And now this 2 G's can be arranged in 2 factorial upon 2 factorial ways. Therefore the total number of arrangements is going to be 6 factorial upon 2 factorial times 2 factorial times 2 factorial upon 2 factorial. So this 6 factorial upon 2 factorial times 2 factorial is related to arranging these 6 units. And this 2 factorial upon 2 factorial is related to arranging these 2 G's. So these 6 units can be arranged among themselves in 6 factorial upon 2 factorial times 2 factorial, and these 2 G's can be arranged among themselves in 2 factorial upon 2 factorial ways. Therefore the total number of ways of arranging the letters of the word singing so that the 2 G's come together is equal to 6 factorial upon 2 factorial times 2 factorial times 2 factorial upon 2 factorial. So you have to write the entire statements like that. And then coming to the third one. So before going into that, we have 6 units. So in these 6 units we have like this. Okay. Relative positions of vowels and consonants are not disturbed. So first let us write down the letters of the word singing, in which S is a consonant, I is an vowel, and G, I, N, G. So we have only two vowels, those are I's, and the remaining are consonants. Now W1 is to arrange I's among themselves. W1 is to arrange I's among themselves. So this we can do it in 2p2 upon 2 factorial ways, or 2 factorial upon 2 factorial ways. And W2 is to arrange consonants. So the consonants here are going to be S, N, G, N, and G. So this I can do it in 5 factorial upon 2 factorial times 2 factorial. So number of ways of completing the task is equal to 5 factorial upon 2 factorial times 2 factorial times 2p2 upon 2 factorial, or 2 factorial upon 2 factorial. These are the total number of ways of arranging so that the consonants and vowels places are not disturbed, or relative positions of the consonants and vowels are not disturbed. The next problem is like this. Find the number of ways of arranging the letters of the word A raised to 4, B raised to 3 and C raised to 5 in its expanded form. So there is nothing in this question. All that you have to do is you have to understand what do you mean by the expansion of this one. A raised to 4, B raised to 3 and C raised to 5. So the expanded form is A raised to 4 means we have 1, 2, 3, 4. And B raised to 3 means we have 3 B's. And C raised to 5 means 1, 2, 3, 4, 5. On the whole we have 4 plus 3 plus 5. 12 letters. So number of ways of arranging these 12 letters is equal to number of ways of arranging is equal to 12 factorial upon 4 factorial times 3 factorial times 5 factorial. So these are the total number of ways of arranging the letters of the word A raised to 4, B raised to 3 and C raised to 5 in its expanded form. Instead of giving this word, they have given it as A raised to 4, B raised to 3 and C raised to 5. This word is same as this one. Okay, let us look into the next one. The next problem is like this. Find the number of 5-digit numbers that can be formed using the digits 1, 1, 2, 2, 3. How many of these numbers are even? So we have to find all 5-digit numbers formed using the digits 1, 1, 2, 2, 3. And we have to find out how many of them are even. So the given digits are 1, 1, 2, 2 and 3. So we have 5 digits. So out of these 5 digits we have 2 1s and we have 2 2s which are identical. So number of 5-digit numbers is equal to 5 factorial upon 2 factorial times 2 factorial. Now we are not interested in this one, we are interested in how many even numbers are there. Number of even numbers. So even number means last blank should be either 2, 4, 6, 8 or 0. So 1, 2, 3, 4, 5. So I can fill the last blank with only 2 because the even numbers in the given list is only 2. So W1 is to arrange the last blank with 2. W1 is to fill the last place with 2, and W2 is to fill the remaining places. So number of ways of doing W1 is equal to 1. I have to fill this last blank with 2's. Since we have 2 2's, but those 2's are identical. So I can fill the last blank with only 1 2, which is one way. Number of ways of doing W2. So after filling the last blank with 1 2, so you'll be left with 2 1's, 1 2 and 3. So we can fill these 4 blanks using 1 1 2 and 3. I can fill these 4 blanks using those 4 objects or 4 letters, 4 digits in 4 factorial by 2 factorial ways. So number of ways of completing the task is equal to 1 times 4 factorial upon 2 factorial. These are the total number of even numbers that can be formed using the digits 1 1 2 2 and 3. Okay, let us move on to the next. There are 4 copies alike of 3 different books. There are 4 copies alike of 3 different books. Find the number of ways of arranging these 12 books in a shelf in a single row. So try to understand the question. There are 4 copies each of 3 different books. So for the sake of simplicity, you can assume that there are 4 mathematics books, 4 physics books and 4 chemistry books. All the 4 mathematics books are alike, all the 4 physics books are alike, and all the 4 chemistry books are alike. Now, the number of ways of arranging these 12 books in a shelf in a single row. Solution. So 4 copies each of 3 different books. So total we have 12 books. So number of ways of arranging is equal to 12 factorial upon 4 factorial times 4 factorial times 4 factorial. So for the sake of simplicity, you can assume that there are 4 physics books, there are 4 chemistry books and 4 mathematics books. All the 4 physics books are alike, all the 4 chemistry books are alike, and all the 4 mathematics books are alike. So we have 3 sets of alike things, and the total number of objects is 12. Therefore, the number of arrangements is equal to 12 factorial upon 4 factorial times 4 factorial times 4 factorial. Next, we have this interesting problem related to rank. I hope you are familiar with rank problems. Now we have to find out the rank of this word EAMCET. Okay, let me read the problem for you. If the letters of the word EAMCET are permuted in all possible ways and the words thus obtained are arranged in dictionary order, then find the rank of the word EAMCET. So in order to solve these kind of problems, the first thing that you have to do is you have to arrange the letters of the word in dictionary order. So first let us write down the letters of the word. The letters of the given word are E, A, M, C, E, T. There are 6 letters. Now we have to the first thing that you have to do is you have to arrange these letters in dictionary order. So the dictionary order here is the first letter is A, and the next letter is E, and the next letter is also E, since we have 2 E's. Sorry. So the first letter is A, and the second letter is C, and the third letter is E, and the fourth letter is also E, and the fifth letter is M, and the sixth letter is T. So these are the letters in dictionary order. Now we have to find the rank of the word EAMCET. So I have to count all the words that begin with A, and I have to count all the words that begin with C, and here I have to be a little bit careful. So before coming into the page which starts with E, I have to count all the words which begin with A, and I have to count all the words which begin with C. So number of words which begin with A. So I can fill the first blank with A. After that I have to fill the remaining 5 blanks. 1, 2, 3, 4, 5. So in how many ways I can fill these 5 blanks using the remaining letters? So this I can do it in 5 factorial upon 2 factorial ways, because the remaining letters are going to be 1C and 2 E's and 1 M and 1 T. So I have to fill these remaining 5 blanks with these remaining 5 letters. I can do this in 5 factorial upon 2 factorial ways. Number of words that begin with A plus number of words that begin with C. So with C also I can have this 5 factorial upon 2 factorial words. So I have completed the number of words that begin with A plus number of words that begin with C. So here I should not count the number of words that begin with E, because our word EAMCET begins with E. So what I have to do here is, so without getting confusion, let us write down the word again, EAMCET, and the dictionary order is going to be ACEEMT. I have counted all the words that begin with A, and I have counted all the words that begin with C, and now I am coming to E. I should not count all the words that begin with E. So rather than counting all the words that begin with E, I can count all the words that begin with EA. As number of words that begin with EA. But my EAMCET starts with EA, so I should not count all the words that begin with EA also. So I have to count all the words that begin with EAC. Number of words that begin with EAC is going to be, so the first EAC, I have to fill these 3 blanks. I can fill these 3 blanks using 1E, 1M and 1T. So I can do it in 3 factorial ways. So number of words that begin with EAC plus number of words that begin with, after EAC I have used E, A and C. After C the next letter is EAE. Number of words that begin with EAE is again equal to 3 factorial. After that, EAC I have completed, M I have completed, E I have completed. Next thing is M plus number of words that begin with EAM. But unfortunately our EAMCET starts with EAM, so I should not count all the words with EAM. So I have to further divide this one. So after M I have to start with C. Number of words that begin with EAMC. But here my word EAMCET starts with EAMC. So what I have to do is, again I have to further divide. So EAMCE. Again my EAMCET starts with EAMCE. Number of votes that begin with EAMCET, which is 1. So rank is equal to, so in the previous page we have 5 factorial upon 2 factorial plus 5 factorial upon 2 factorial plus 5 factorial upon 2 factorial plus, so 3 factorial plus 3 factorial plus 1. So this is my rank of the word EAMCET. So let me explain the problem again for you. We have to find the rank of the word EAMCET. So for this, what we have to do is, first you have to arrange the given letters in dictionary order. And the dictionary order here is ACEEMT. Now we have to find the rank of this word EAMCET. So my EAMCET starts with E. So I can count all the words that begin with A, and I can count all the words that begin with C. Number of words that begin with A is going to be 5 factorial upon 2 factorial, and number of words that begin with C is also equal to 5 factorial upon 2 factorial. Now I cannot count all the words that begin with E, because my required word EAMCET starts with E. So what I have to do is, I have to make the further division. So I can count all the words that begin with EA. But my EAMCET starts with EA. So I cannot count all the words that begin with EA. So I can count all the words that begin with EAC. So number of words that begin with EAC is equal to 3 factorial. After EAC, I have EA, again E. Number of words that begin with EAE is again 3 factorial. After EAE, the next thing is EAM. I can count all the words that begin with EAM, but unfortunately my EAMCET starts with EAM. So I cannot count all the words that begin with EAM. I can count all the words that begin with EAM. The next thing is C. I cannot count all the words that begin with EAMC, because my EAMCET starts with EAMC. So I have to count all the words that begin with EAMCE. Again the same thing. EAMCET starts with EAMCE. So I have to count all the words that begin with EAMCET. The number of words that begin with EAMCET is going to be 1. Therefore the rank of the word EAMCET is equal to 5 factorial upon 2 factorial plus 5 factorial upon 2 factorial plus 3 factorial plus 3 factorial plus 1. Or else the number of rank of the word is equal to number of words that begin with A plus number of words that begin with C plus number of words that begin with EAC plus number of words that begin with EAE plus number of words that begin with EAMCET. So no need to expand all these things, you can just leave the answer as it is. So with this we have completed all example problems.